Hello students, I am Sachitrakar. Welcome to Cars Physics. We are continuing moving charge and magnetism, and this is my lecture number 7 on the chapter. In previous lecture, we have discussed the force on a moving charge in a magnetic field, and as it is found from experiment that when a charge moves in a magnetic field, then it experiences a force. When a charge moves in a magnetic field, then it experiences a force, and the force is given as magnitude of charge into cross product of velocity of charge particle and magnetic field. And as we have discussed, when a charge moves in a magnetic field, experiences a force, it means a charge at rest in magnetic field doesn't experience any force. Okay? This is basic difference between electric field and magnetic field. If a charge is either at rest or in motion in an electric field, then it experiences a force. But in magnetic field, in case of magnetic field, only a moving charge experiences a force. Okay. Also, there are conditions. What should be angle between velocity of charge particle and magnetic field? And as we have discussed, the magnitude of force is equal to QVB sin theta. And theta is angle between velocity of charge particle and magnetic field. Thus, it is concluded that if a charge particle moves either parallel or anti-parallel to the magnetic field, means if value of theta is either 0 degree or 180 degree, then the charge particle experiences no force and nature of trajectory is a straight line. Of course, we have discussed, if a charge moves in a magnetic field, means if angle between velocity and magnetic field, velocity of charge particle and magnetic field is 90 degree. If a charge moves perpendicularly in a magnetic field, then sin 90 degree is 1, then force is maximum, and in that case, nature of trajectory is circular. Of course, we have discussed, if a charge particle moves at any angle except 0 degree, 180 degree and 90 degree. If a charge particle moves at any angle in a magnetic field, then it moves in a helical path. Are you clear? Is it clear? Okay. And we have discussed up to this motion of charge particle in magnetic field. Of course, we have discussed all the cases. And in this class, in this lecture, we will discuss force on current carrying conductor. Force on current carrying conductor in a magnetic field. Let's see. So this is force experienced by a charge particle. Magnitude of charge is Q. Let's consider an uniform magnetic field. And here we are considering magnetic field in inward direction, means perpendicular to this plane. The uniform magnetic field is B. Let's consider a conductor is placed in the magnetic field, and this conductor is connected to the terminals of a cell, positive and negative. Okay. So when a conductor, the basic concept, when a conductor is connected between terminals of a cell, as we know, the free electrons present in the conductor move from low potential to high potential, and conventionally we do assume that equal quantum of positive charge, means positons, move from high potential to low potential, and as we have discussed in current electricity, direction of conventional current is from high potential to low potential, means as per convention, equal amount of positive charge flow from high potential to low potential, and magnitude of current is also equals to Q by T or Ne by T. This is conventional flow of current along the direction of flow of positive charge as per our convention. Okay. So, now let's consider as per our convention a positive charge, let Q, is moving in the conductor from high potential to low potential with a velocity v. Okay. The conventional flow of charge is flow of positive charge which flows from high potential to low potential. That's in the direction of conventional current. Okay. Let's consider a positive charge Q is flowing with a velocity v, means current flowing in this conductor. This is conventional current. Flow of current means flow of charge, as we have discussed in current electricity. What is meant by current? What is meant by current? Current means flow of charge. Current means flow of charge. And magnitude of current or strength of current is amount of charge flowing per unit time. But basic definition of current is flow of charge. So if a charge flows, then we do say current is flowing in the conductor. Let's consider a positive charge is moving inside the conductor, means current is flowing in the conductor. Let's consider flow of this positive charge. As we have discussed, if a charge moves in a magnetic field, then it experiences a force. Thus it implies that flow of charge is current, flow of charge is current. Thus it implies that if a current carrying conductor placed in a magnetic field, then it experiences a force. Clear? When a charge moves in a magnetic field, it experiences a force, and motion of charge in magnetic field experiences a force. So, moving charge, if charge moves, then it is equivalent to current. Then it may be concluded that if a current carrying conductor, means current is flowing in the conductor, it means charge is flowing in the conductor. If a current carrying conductor placed in a magnetic field, then it experiences a force. Okay. Let's find first derivation of force experienced by a current carrying conductor or current carrying wire in a magnetic field. Then we will have some basic numericals on this concept. Right? Okay. Okay, you have chance to ask questions. So far as you are silent, so let's discuss first the concept. I will discuss some questions, then you are allowed to ask some questions. Okay, I know. Let's consider a magnetic field, uniform magnetic field. Here I have taken magnetic field inwards, means perpendicular to this plane, and direction is inwards. We may take also outward magnetic field, and here magnetic field is uniform. Let strength of magnetic field is B. Okay, you may take like this, or you may take dot fields, uniform magnetic field. Here magnetic field is in outward direction. Okay, or in simpler way, I am representing the magnetic field on this plane. You just imagine this is north pole of a magnet and this is south pole of a magnet. So magnetic field lines are from north pole to south pole. Okay, I am representing first magnetic field on the plane of this whiteboard. Okay, so this is the direction of magnetic field B, and we are representing an uniform magnetic field, and as you know, if field lines are parallel and equidistant, then magnetic field is uniform. Okay, let's represent an uniform magnetic field, and strength of magnetic field is B. Okay. Now let's consider this is a current carrying conductor. This is a current carrying conductor placed in the magnetic field. Okay, this is a current carrying conductor placed in the magnetic field, and area of cross section of the conductor is A. This is direction of magnetic field. This is length of conductor, and angle is let theta. Means current carrying conductor makes an angle theta with magnetic field. Is it clear? Okay. So current is flowing in this conductor left. This is connected to negative terminal and this is connected to positive terminal. So obviously electrons flow from low potential to high potential, and equal amount of positive charge flow from high potential to low potential. And as we know, at a given temperature, free electrons move with velocity, drift velocity Vt. Of course, this positive charge will assume moving with same speed, means with same velocity but in opposite direction. Okay, so this is flow of positive charge, means flow of conventional current. Current is flowing in this conductor. Now let's consider an elemental length, a very small length. Very small length. Very small length of the conductor, and this length is let dl. Let's consider an elemental length of the conductor dl, but total length of the conductor is l. Total length of the conductor is l, and area of cross section of the conductor is A. Then volume of elemental section. Volume of elemental section is, area of cross section is A, this is also A, and length is dl. Volume of elemental section is A into dl. Okay, and as we know, let n is number density of charge, means free electrons. Number density of free electrons means n is number of free electrons per unit volume of the conductor, and as we have assumed, equal amount of positive charge flow from high potential to low potential. So number of free electrons may be assumed to be equal to number of positive charges. So n is number density, number of charges per unit volume, and here volume is L. Then total number of charges is n into AD. N is number density, number of free electrons per unit volume, and n total volume means volume of elemental section is ADL. This is number of total charge. We are considering positive charge. Then total charge. This is number of charges, and total charge is n into ADL into charge is E. This is total charge, and this is Q. Total charge is Q. Is it clear? Total charge is n ADL into E. Okay, and as we know, force is equal to, as per our formula, Q into V cross B, and that may be taken as Q V B sin theta. For this elemental length of conductor, let's consider force on the charges is dF. For total length of conductor, force will be F. Now, in accordance with this formula, force is Q. Here Q is N A dl into E. This is Q. Then velocity V is drift velocity. Q V. Magnetic field is B into sin theta. So we have got our formula QVB sin theta. So here V is a drift velocity. So this is the dF force on this elemental section of conductor. Okay. Then to get total force means total force on the total length of the conductor. Let's integrate both sides. Integration of dF is equal to, you see, MAEVD sin theta. All are constants, and integration of dl. Integration of dl, then what is dl? It is very important, of course. Integration of dl is a L, but what is integration of dl? Very important to know it. Integration of dl represents what? Integration of dl represents, in general you may say integration of dl means total length of the conductor. Yes, this is correct, but the meaning is dl represents vector sum of all elements, from initial to final position of the conductor. This is important. dl, integration of the dl is small part of the conductor, but integration of dl means total length. Integration of dl represents vector sum of all elements from initial to final position of conductor. See, we have taken a straight conductor. I will discuss it in later stage while solving questions. Okay. So, dl represents vector sum of all elements from initial to final position of the conductor. Then, obviously, integration of df is MAEVD. Integration of dl is L, and finally we may put sin theta. This is formula for force. I am writing here. Force is equal to MAEVD L, velocity, drift velocity, into total length of conductor L, into sin theta. This is the expression for force experienced by the current carrying conductor, but derivation is left. You see, NAEVD. Oh, I have left this B. NAEVD, current is equal to, we know it from current electricity, NAEVD, I is equal to NAEVD. Then final formula for force is, in place of NAEVD, I can write current I, L, B, sin theta. This is magnitude of force. And in vector form, you may write current I, then L, B, sin theta, we may write L cross B. Where theta is angle between L and B. Then what is direction of length? Direction of length is taken along the direction of conventional current. Direction of length is taken along the direction of flow of current. Current flows from high potential to low potential, and direction of length is taken along the direction of flow of current. Okay. And in vector form, F is equal to I into L cross B. By using this relation, we can calculate direction of force either by taking the direction of cross product of L and B, or by using Fleming's right hand rule, or by using Fleming's left hand rule. Okay. And as per right hand rule, the thumb represents motion of charge carrier, means direction of velocity of charge carrier, thumb. And these all these fingers, 4 fingers, represent direction of magnetic field, and palm represents direction of force. Okay, you see, this is thumb, these are 4 fingers. Okay, thumb represents motion of charge, means directly speaking velocity of charge, v. And these fingers represents direction of magnetic field, and palm represents direction of force. Or simply you may say the cross product of L and B shows direction of force, or you may use Fleming's left hand rule. The 4 finger, middle finger and thumb are stretched in mutually perpendicular direction. 4 finger, middle finger and thumb, okay, are stretched in mutually perpendicular direction. Here 4 finger represents direction of magnetic field, middle finger represents direction of current, means flow of charge, velocity of charge, and thumb represents force. You may use directly this relation L cross V, direction of L cross V is equal to direction of force, or right hand palm rule, or left hand rule. Okay, is it clear? Is it clear to you all? Fine. Okay, these are the relations. Then some fundamental questions on the basis of force on current carrying wire in a magnetic field. Okay, just see. Suppose I am taking, this is a magnetic field, uniform magnetic field, dot field. In this field is directed outwards, means perpendicular to this plane. Here magnetic field is B. Okay, and here this is a line parallel to the surface. Suppose this is x-axis, and a current carrying conductor lies like this. Current is I, length is L, and here magnetic field is B. Let this angle is theta. Then it is asked, what is force on this conductor? Force is, magnitude of force is I L V sin theta. This is magnitude of force. Then in this case, the important thing is to know what is value of theta. Theta is angle between L and B, and direction of length is taken along the direction of flow of current, and direction of magnetic field is outward. Direction of magnetic field is outward, and this is direction of current, this is direction of length. So this theta is meaningless in this case, and here theta is 90 degrees. This is direction of magnetic field, and this is direction of length. Length is parallel to the plane, and magnetic field is perpendicular to the plane. Thus theta is 90 degrees. The field may be dot field or may be cross field. If a current carrying wire is lying parallel to the plane and magnetic field may be outward or may be inward, then theta is 90 degrees, and in this case force is equal to ILB, that is maximum. Okay, suppose this is a magnetic field like this, and a current carrying conductor is kept like this, in which current is flowing. This is L, and here magnetic field is B. Here direction of length is along the direction of current, and theta is 0 degree. And in next case, this is direction of magnetic field, and this is current carrying conductor. Let current is flowing along this direction, and this is direction of length, this is direction of magnetic field. Direction of length is along the direction of flow of current, and here this is direction of magnetic field. Here angle between magnetic field and length is 180 degree. Then another illustration, this may be appropriate also. This is direction of magnetic field, and this is a current carrying conductor. placed in the magnetic field. Let current is flowing in this conductor. Length of conductor is along the direction of flow of current, and here theta is 90 degree. Then in these two cases, force on the current carrying conductor is 0 or minimum. The similar discussion. If the current carrying conductor is either parallel or anti-parallel to the direction of magnetic field, then force experienced by the conductor is 0. If the current carrying conductor is placed perpendicular to the direction of magnetic field, then force is equal to ILB, that is maximum. Again, direction in this case, this is direction of length, this is direction of B, L cross B inverse. L cross B, just use cross product, it is easier. L cross B inverse, force is inverse. And here in this case, this is length, direction of length, and this is direction of magnetic field. See, this is direction of length, and outward, in outward direction, that is magnetic field, L cross B, this is outward, L cross B means force is in this direction, downward direction. This is L, and magnetic field outward, L cross B, force is downward. If the field were dot field, means if the magnetic field were inwards, then this is length, magnetic field inward, this is length, magnetic field inward. Suppose you are taking a cross field. This is current carrying conductor, current is I, and length, direction of length is along the direction of flow of current, and this is B. Then how to find direction of force? L cross B, this is L, and B is inwards, L cross B, then force is perpendicular to the length, force is upward, and this, in this case, force is downward. Very easy. You may use the cross product rule, or you may use right hand palm rule, or you may use left hand rule. Okay, very good. Then again some illustrations and very important. Okay, suppose this is a semicircular coil. Current flowing in this coil is I. Radius of semicircle is, this is center, radius of semicircle is R. This semicircular current carrying coil is placed in an uniform magnetic field, B. Okay. Or I am taking first, you may take like this also, changing. I will come to this point after discussing it. It is easier to feel it. Suppose this is direction of magnetic field. This is direction of magnetic field parallel to the plane, and you just keep a semicircle carrying current I, and radius of the semicircular current carrying wire is R. Then we have to find what is force on this semicircular coil. Okay. Then as per our formula, F is equal to ILB sin theta. ILB sin theta. Here what is length? See, in previous discussion I have shown what is formula for DF. Formula for DF, integration of DF is equal to NI VD B sin theta into integration of DL. Then what is DL? DL is vector sum of elements of the coil from initial to final position. Initial position is let C, final position is D. Okay, vector sum of DL, vector sum of DL. So in this case, integration of DL is L, AP is equal to NI VD B sin theta into L. What is L? L is vector sum of elemental parts. So vector sum of elemental part is displacement. From not directly displacement, we do understand like this. If this is the total length, this is initial and this is final, sum of elemental sections in a given direction is from C to D and this length is 2r. Again, angle between elemental length, length 2r, here length is 2r, and magnetic field along this direction, and in this case theta is 0 degree. This is direction of length, this is direction of magnetic field, theta is 0, so force is equal to ILB sine 0, that's equals to 0. Is it clear? Okay. Next, see, suppose this is the same semicircular coil, current flowing is I, this is C, this is D, this is D. Again, sum of DL is 2R if radius is R. Okay, and here in this case, this is the direction of magnetic field. This is the direction of magnetic field. In this case, this is length, this is direction of magnetic field, and angle is 90 degree, and force is equal to, magnitude of force is equal to ILB sine 90, and this is equals to ILB, and here I, in place of length we can take 2R into B. Okay, DL, sum of DL is L and sum of DL is vector sum of elemental lengths from initial to final position. Okay, these are two diagrams, and then let's take dot or cross field for same semicircular part of where. Let's consider either dot or cross field. Let's take a dot field. Magnetic field is directed outward. Magnetic field is B, directed outward. Okay. A semicircular wire is kept in the magnetic field, current flowing is I, and radius of the semicircle is R. Then sum of elemental length is from C to D, that length is L. L is equal to 2R. And here, angle between length and magnetic field, theta is 90 degree. Theta is 90 degree. This is direction of length and this is direction of magnetic field. This is direction of length, this is direction of magnetic field. Then again force is equal to, magnitude of force is equal to IL 2R into B into sine 90, and force is equal to I into 2L into B. Okay, you can find the direction. This is direction of length, this is direction of magnetic field, L cross B. This is direction of length parallel to the plane, this is direction of magnetic field, L cross B. Direction is inwards. L cross B, direction of force is downward. L cross B, force is downward. Okay. So these are some illustrations how to determine the force. Okay. Now, some fundamental numericals. You see. Suppose, okay, this is a current carrying coil wire, but closed loop, current flowing is I, placed in a magnetic field. Let's take cross field, placed in a magnetic field is B. Then as we know, integration of df is equal to NI VD B sin theta into integration of df. Then what is dl? What is dl? Yes, what is dl? dl is vector sum of elemental lengths. So vector sum of elemental length for a closed path, vector sum of elemental length for a closed path is 0. So integration of df is f. So f is equal to 0. Thus it is very clear, and you should remember that. You should remember that. If a closed loop of conductor carrying current placed in a magnetic field, then force experienced by the closed loop carrying current is always 0. If the magnetic field be either inward or outward. This is uniform magnetic field. The shape of coil, whatever may be the shape of coil, whatever may be the shape of coil, you may take shape is rectangular or square, current is I. Or you may take shape is a triangle, current flowing is I. Okay. Or you may take shape is circular, current flowing is I. In all cases, for a closed loop placed in uniform magnetic field, sum of elemental length means vector sum of elemental length is 0. So force experienced by the closed loop is 0. Okay. Fine. Very good. Then a numerical, very easy numerical, fundamental numerical question. A wire straight wire, you may take a straight wire, of length 2 meters. A straight wire of length, let's take 1.5 meter for easy calculation. A straight wire of length 1.5 meter and of mass 200 gram. A straight wire of length 1.5 meter and of mass 200 gram carries current of 4 ampere. Carries current of 4 ampere is held in space by the effect of magnetic field, so that it neither rises nor falls. So find magnitude of magnetic field. Okay. Simply, a straight wire of length, let L, of mass M, is held in space. I am holding this, I am not holding, it is just left and it remains in space so that it neither falls nor rises. This is a current carrying wire. So, this wire is in equilibrium in space. It neither rises nor falls by the effect of magnetic field. Then we have to calculate what is magnitude of field. Obviously, in this case, angle between direction of length and direction of magnetic field is 90 degree. Okay, because force experienced by the wire must be in upward direction, and weight in downward direction. So, force experienced by the current carrying wire balances the weight of the wire. So, magnitude of force experienced by a wire is equal to magnitude of weight, means weight of the wire. Then, here force is equal to I L B sine 90 is 1. Then for equilibrium, I L B is equal to mg and magnitude of magnetic field is simply mg by I L. So direct it may come in objective based or MCQ questions, and now calculation. Magnitude of magnetic field, mass is 200 gram, 200 into 10 to the power minus 3 kg. Let's take G, 10 meter per second square, and magnitude of current is 4 ampere and length is 1.5, and calculating it you will get 0.325 Tesla. 0.325 Tesla. Straightway is held in equilibrium in space by the effect of magnetic field, means force experienced by the magnetic field. Okay. Of course, in this type of question, angle, in this case angle 90 degree, or any other case, in general force may be asked. What is the force of ILB sin theta? Suppose this is a wire bent like this. This is a wire bent like this. Okay. Let this angle is 60 degree. This angle is also 60 degree. This wire carries current I. Same current is flowing in this wire. Length of this part is L. This part is also L. Both the parts have same length, L and L. And this wire is placed in a magnetic field. This wire is placed in a magnetic field. And obviously we are taking uniform magnetic field. All these cases we are considering uniform magnetic field. Let be. Direction of magnetic field is inwards, and we have to find what is total force on the wire. In simpler way, in very simpler way, you can solve it. Okay. What is meant by integration of dl? Integration of dl is vector sum of lengths from initial to final point. From initial to final point. So, integration of dl is L and this is L. This is direction of length. Of course, this length is L, this length is L. Then we have to find this length. Let this is L dash. This is integration of dl. This is direction of L dash and this is direction of magnetic field, and here theta is 90 degree. Then force is integration of dl, vector sum of elemental lengths from initial to final position. This is initial, this is final. Thus this is vector sum of elemental lengths of all the parts of conductor. This length is L dash. Then force is equal to I, current is I, length is L dash B sine 90. Then force is equal to I L dash B. Then force is equal to I L dash B. I will show in different form also. I L dash B. Then our aim is to get L dash C. This angle is 90 degree. This is L. So this part, let this is O. BO is equal to L sine 60. This is B. This is L. This angle is 60. So this is L sine 60. And obviously OB is L sine 60, and obviously OC is also L sine 60. This angle is also 90 and this is also length. So total length. So L dash is equal to OB plus OC. So that is equal to L sine 60 plus L sine 60 is equal to 2L sine 60. And this comes 2L into root 3 by 2 to get cancelled, and this is equals to root 3L. Then force is equal to I into root 3L into B. This is your answer. Okay, magnitude of force, and this is can be stated in different way also, in some lengthier way also. Just see the method. Just see the method. You just remember the answer. This is answer for force. This is answer for force. Force is equal to magnitude of force I into root 3 into V. The same diagram I am repeating in some lengthier way, but follow this while doing numericals in competitive. Magnetic field inwards. Magnetic field inwards. Inward magnetic field is B. Current flowing is I. This part is length L. Current flowing is I. This part also has length L. This angle is 60 degree. This angle is 60 degree. So, direction of length is along the direction of flow of current. This is direction of length, and this is inward is direction of magnetic field L cross B. L cross B. This is direction of force F. And for this is direction of length inward. Magnetic field is inward, L cross B. Again, force is along this direction. This is direction of force. So we have considered two parts of conductor, but it is a single conductor. In this part, this is direction of force. In this part, this is direction of force. Thus produce it. Thus produce it. This is the angle between two forces. This is angle between two forces. You know vector analysis. Okay. This is angle between two forces. Okay. Then this angle is 60. Draw a line parallel. Draw a line parallel to this line. If this angle is 60 degree, obviously this angle is 60 degree. If this angle is 60 degree, then obviously this angle is 60 degree. But this total angle is 90. This total angle is 90. So this angle is 30 degree, and this angle is also 30. Is it clear? This is 30, this is 30, this is 60, this is 60. Okay. Again, this angle is 90. Force is perpendicular to length. For this triangle, this is 60, this is 90. So this angle is 30 degree. For this triangle, this is also 90, this is 60. So this angle is also 30 degree. Thus bring the forces outside. This is the force. This is the force. And total angle between the forces is 60 degree. And this is direction of resultant force. Of course, the representation will be like this. This is direction of resultant force. F. 30, 30, F. So this is direction of resultant force. You know from vector. If magnitude of two vectors is same, then their resultant must bisect the angle between the vectors. Total angle is 60 degree. Then force bisects the angle. And here, magnitude of resultant force is square root of F square plus F square plus 2 F cos 60. And this is equals to root of 2F square plus 2F square cos 60 is 1 by 2. So this comes root over 3F square, and the answer is root 3F. And force on each conductor is root over root 3. F is equal to current is I, length is L, magnetic field is B. This is the answer, and this is the previously found answer. Both are same. Now choice is yours. Okay. The next question. The next question. Very good question. Of course, let's do another small bit. Suppose this is a wire like this. Like this. A, C, D, E. Current flowing is I. Current flowing is I. current flowing is I. Placed in a magnetic field. Okay, let each side of the square is 2 meter. This side is also 2 meter. And magnitude of current, you may take any value of current. Let's take current is equal to 3 ampere. Okay, and magnitude of magnetic field, here magnetic field is B, directed inwards, you may take any value of B. Let's take B is equal to 12 Tesla. Let's take any value. Then what is the total force on this current carrying conductors? See, total force is equal to force on ACD plus force on AD plus force on AED. But see, for ACD, this is a curved path. Initial point is A, final point is D. Okay, and integration of dl is vector sum of elements of the conductor from initial to final. So ACD, force on ACD is same as that of force on AD. This is initial, this is final. And similarly, force on AED, this is initial, this is final. Then force on AED is also force on AD. Then final answer is 3 into force on AD. This is resultant force on AD. And length of AD is 2√2 meter. This is 2 meter. This is 2 meter. This is 90. Okay. This is 90. Okay. This is a square obviously. So diagonal is 2√2. Length is 2√2. Magnetic field is inward. And angle between length and magnetic field is 90 degree. Magnetic field inward and length is along the diagonal. Then this is equals to 3. Force is equal to ILB sine 90. Then 3. Current is 3 ampere. Length is 2√2. This length of AD, 2√2 meter. Sine 90 is 1. Then magnetic field we have taken 12 Tesla. Then calculating 3 into 3, 9, 9 into 12. Sorry, 18 into 12 √2 Newton. Now calculation years, very easy. Okay. Then another concept, very good concept and a beautiful question also, very fine question. See, question is like this. This is a magnetic field, uniform magnetic field. This is an uniform magnetic field. Okay, let strength of magnetic field is B. Strength of magnetic field B and directed inwards. Suppose a current carrying loop. Suppose a current carrying loop is placed in a magnetic field. Okay, then what will happen to the shape of loop? This is first question. If a current carrying loop is placed in a magnetic field, obviously we know for a closed loop placed in magnetic field carrying current, then resulting force on it may be 0. Resulting force on it is 0. But the question arises, if a loop is placed, an irregular shape of loop carrying current is placed in uniform magnetic field perpendicular to the plane of loop, then what will be its final shape? And answer is circular. Answer is circular. Why? Because each element of the current carrying loop will experience a force. See, suppose I am taking this part of length. This part of length is dl, current is I. This is direction of length, this is direction of current, and dl cross B, force is outward. dl. If you consider this part of length, this is dl, this is dl, okay, this is dl, and dl cross B, this is dl. And magnetic field is inward. This is direction of dl. magnetic field is inward, dl cross B force is again outward. Here is outward. And every element will experience a force in outward direction df, 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 and finally it will open to a circle. Finally, it will open to a circle and each element will experience a force df, 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 df. Symmetrically, you may represent these forces df, 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 etc. If an irregular loop carrying current placed in magnetic field in such a way that plane of loop is perpendicular to magnetic field, then it will open to a circle. Then, from numerical point of view, it may be asked, what is tension in the elemental part or a tension in the loop. We will consider each elemental part and we will find tension in the loop. Okay. Let's consider a small part of the loop. This is a small part of the loop. Very small. Looks large, but I am taking a very small part of loop. This is a very small part of loop. This part. Just join this. This is center. I am extending the diagram to have a clear idea. Current is flowing in it. Let current is I. And this is direction of magnetic field. As we have already represented, this is direction of magnetic field. Okay. Length of this part is dl. Length of this part is dl. Thus bisect it. This is center O, this is center O. The same part. This part is taken to this point here. Okay. Current flowing is I. Total length is dl. Total length is dl. I have taken dl. Okay. And when it will experience a force in outward direction, this part will experience tension. This part will experience tension. So, this angle is very small, this angle is also very small. Okay, let's take this angle is theta and this angle is theta and draw a line tangential to the surface. Of course, this angle is very small, let's take theta. This angle is very small, let's take theta. Then now, direction of force on this elemental part dl is df. In outward direction as we have observed. Then the reason of this tension along this direction component of tension is T cos theta and along this direction component of tension is T sin theta. And for this tension component of tension along this direction is T cos theta and along this direction is T sin theta. So this total force becomes 2T sin theta. T cos theta are equal in magnitude, opposite in direction. So, resulting value of T cos theta and T cos theta is 0. Both cancel each other. Thus, only force is the components, rectangular components of two tensions is 2T sin theta and upward force is D. Is it clear? Then for equilibrium, upward force dF is equal to 2T sin theta. Upward force dl is equal to 2T sin theta, or you may write 2T sin theta is equal to upward force dl. But length of this part is dl. And angle between dl means flow of current. You may take tangential direction angle between dl and magnetic field is 90 degree and 2T sin theta is equal to I dl B sine 90 degree. Length is dl. Length is dl. So finally, 2t sine theta is equal to I dl into b. Is it clear? Is it clear? This is length. We will calculate for whole length. This is the dl, elemental part of the closed loop. This is dl. Okay. Then magnetic field is B, elemental length is dl, and 2t sine theta. If this angle is very small, for small angle, we may take sine theta as theta. Then it is 2t into theta is equal to I dl into b. 2t into theta is equal to I dl into b. Is it clear? Okay. Fine. Then theta, what is theta? What is theta? Theta is equal to, see, angle is too small. The angle is too small, then you may take theta is equal to dl by 2, this part, dl by 2, divided by dl by 2 divided by radius. Radius of the circle, let's take r, then theta is equal to, I am writing here, theta is equal to dl by 2r. This part is dl by 2, radius is r, this is sine theta. Sine theta may be taken as perpendicular upon base. If this is very small, then this will be perpendicular. This angle is 90 degree, very simple. Then theta is equal to dl by r. Okay. Then here 2t into theta is equal to I dlb. Then just put here in place of theta 2t into dl by 2r is equal to I dl into b. dl get cancelled, 2 get cancelled, then tension is equal to I b r. Tension is equal to I b r, and also again you may calculate it. If this is open to a circle, then 2 pi r. Okay, radius is capital R, I b r. 2 pi r is total length. Total length is let L. Total length is L. Then r is equal to L by 2 pi. And here you can put it. T is equal to I b L by 2 pi. I b L by 2 pi. And if value of current, value of magnetic field, and radius, all these things are given. Sorry, not radius, length of total coil is given, then we can calculate tension. Okay, very important and application question also. Fine. Now it's your chance to ask me question. Okay, just wait. Have you read the question? Okay, fine. Very good. I am writing your question. A good question. A metal rod. This is a very good question from previous competitive. A metal rod of mass. 10 gram and length 25 centimeter is suspended by 2 springs. Suspended by 2 springs. The springs are extended by 4 centimeter when a current of 20 ampere flows through the rod, it rises by 1 centimeter. Calculate magnitude of magnetic field. Good question. We have to calculate the value of magnetic field, and it is your diagram is also given. Okay, and the basic, what is the basic concept? Where there is current, there is magnetic field, and as per your question, I know the diagram. Okay, this is support. This is support. Two springs are there. And a rod is suspended on the two springs. This is a rod. Weight of the rod acts in vertically downward direction, and length of the rod is 25 centimeter, and mass is given. Okay, and here there is a source of EMF, and this is a switch. Okay, now there is no current is flowing in the system, flowing in the conductor. Let spring constant is K for both the springs, and when there is no current, okay, then see, the rod pulls the spring in downward direction, the spring is elongated, the spring force or restoring force acts in upward direction. Those are tensions in the spring. Tension in each spring, let T naught. And as we know, tension is equal to a constant into elongation. Let the initial elongation is 4 centimeter. Let's take x0. And here, tension, here there is tension T naught, here there is tension T naught, and 2 T naught. 2 T0 is total upward force, and total downward force is M. Okay, is it clear? When current flows, then magnetic field is produced. And the body rises by, the rod rises by 1 centimeter, it rises. Because force is experienced by the rod. So that it rises up. How much it is rises is 1 centimeter. Now current is flowing. When current flows, when there is no current, these are the relations. When current flows, then let tension in the spring is T. Previously tension was T0, now tension is T. And now let elongation is x and T is equal to kx. Now total upward force, obviously 2T, T and T, 2T, plus force due to magnetic field on current carrying conductor, that is equals to ILB, total upward force is equal to total downward force, again mg. Okay, these are two outputs when current is flowing and when current is not flowing. Now it is easier. Let's take T divided by T naught. T divided by T naught, that's equals to Kx divided by Kx naught, that is equals to x by x naught. Okay, and from this we can get T is equal to mg minus ILB divided by 2. And from here T naught is equal to mg by 2. Again T by T naught T is equal to mg minus ILB whole divided by 2. In place of T naught we can write mg divided by 2. 2 get cancelled and it will come mg minus ILB divided by mg. So T divided by T naught. T divided by T naught. In place of T, okay. T divided by T naught is equal to mg by mg is 1 minus ILB by mg. Minus ILB by mg, and in place of T by T naught, in place of T by T naught we can put x by x naught. Now it is simpler to solve and to get B, okay, and B will be equals to, just I am taking direct step, B is equal to mg by IL, just bring not directly I am taking like this, or otherwise you will feel difficult. ILB by mg, bring it to left side, is equal to 1 minus x divided by x naught, and this implies B is equal to mg by IL into 1 minus x by x naught. Now you solve for B. And you have given your answer. No, you have not given your answer. Calculate this, you will get your answer. Okay. Initial elongation is 4, x is 4. It rises by 1 centimeter. Then now elongation is 3. Then x is 3, x naught is 4. Mass is given 10 gram, convert it into kg. Length is given in centimeter, convert it into meter. G take G 10, and current flowing is 20 ampere, and solve it. It's too easy. Thanks, my dear children. This is end of lecture 7. In next lecture, again we will meet with some beautiful concepts. Thanks.